May as well get started. So we're happy to have Mingda Li from the Department of Nuclear Science and Engineering at MIT visiting us today. Mingda got his PhD at MIT in the Nuclear Science and Engineering Department, and then did a postdoc at MIT in the Mechanical Engineering Department, and then became a faculty member at MIT back in the Nuclear Science and Engineering Department. Sort of throughout his career, Mingda has done a lot of nice work using neutron scattering and X-ray scattering and some material science to help us understand some interesting things about topological semi-metals and other magnetic states of matter. But Mingda is also kind of half theorist and half experimentalist. So sort of more recently, although I guess time goes fast, so it's maybe not that recently, has been doing a lot of work trying to understand how we can use all of these amazing tools in machine learning to help us do quantum materials research better. And he's really one of the people who's really pushing that in our field, I think, the most. So we're very happy to have you here today, Mingda, to talk to us a little bit about what you're doing. Thanks so much.
Thank you, Cam, and thank you everyone for joining for today's seminar. I feel deeply honored coming here. And so every year when my department, the Nuclear Science and Engineering, try to recruit new students, and in the interview we always ask one question, that's like a spoil alert, and how many years and do you have on this rest of this oil and the gas supply of the world? Based on the current consumption, this speed, that's roughly like 50 years. So to some extent, and we are kind of doomed because the fossil fuels are burning just so fast. And then people are calling for like more efficient architectures at various levels, particularly for materials level, to drive the future technology. For quantum materials in particular, even for very weak quantum effects, that can already improve a lot in terms of energy efficiency. Like the example for the GMR, and if you only do like the two magnetic layer parallel or anti-parallel to each other, and then there's like a magnetoresistance that already changes by orders of magnitude, that drives this huge this increase of this hard drive capacity, and later it's driven by another effect of TMR from there. On the other hand, even for just a simple semiconductor digital structures, and that is a blue light LED, because 20% of the whole global electricity is used for lighting, and that energy, this saving is also tremendous. But imagine these are just very simple quantum materials using very simple rules. There are many more challenges that yet to be addressed. One of them people are saying is the so-called waste. So imagine people are talking about various kinds of this clean energy, nuclear included, but then after going through different sectors, polarized somehow the resolution is not so high, different sectors such as transportation, industry, or residential, eventually only 1/3 of all the generated energy will be used, called service, and then 2/3 will be end up as waste heat. Imagine that if you can reuse this waste heat, such as the field in thermoelectrics, and then how much energy saving can we get also from all this there? There's something even crazier going on related to the computing energy consumption. Back about 9 years ago, there is an SIA report and claiming that the computing energy consumption is actually growing exponentially. It's not quite that surprising if you follow the Moore's law, but thinking about if you really are calculating, assuming the world energy production is a constant, then by as early as 2040, then the whole this global energy production will be used just for computing. Definitely need some fundamental change for more efficient computation. So people were thinking this is too scary and exponential growth may never true. But look at what really happened in the past few years. This is another report from Nature, also back in a few years ago. And because there are a new need driven by the computing, as we all know, machine learning data center. That's kind of this statistics is like we are doing machine learning in order to find the material to be more efficient. But then on the contrary, machine learning also consume very much energy, like the data center. Right now it's about 1%, but then in 5 years it could be as much as 80% of all the global electricity will be used to just power data centers. So that's why it won't be a too surprise for you to see like Google purchased this nuclear power plants very recently, same as Amazon or even Microsoft. They powered this 3 miles island, and that had been a nuclear accident, but one of the reactor was intact. But then they want to restart them and to power the data centers. So before we introduce the content for today, here is one of the state-of-the-art this machine learning, also from the same company as OpenAI and the ChatGPT, and called O1. So this model claims to do as good as the PhD students in terms of the exam taking. And so this is the many benchmark the score. Thinking about the PhD level, like a physics exam, it can just pass even 90%. So that was very, very impressive. So I was very curious when it first started and did some quick tests. Imagine that many people here, they are doing theory, and just the question is, can we just write down this second quantized form and for the light matter interaction, and from the first quantized form, the A dot P. And then just do this step by step, writing down the Hamiltonian, and then write down this quantized operator form for the vector potential. And then from there, and eventually they can just substitute the single electrons orbital, finally write down this interaction, this Hamiltonian. That seems to be very good until if you are careful enough to look at the coefficients, then there is something going on here. There is some kind of the mixture between different units. Apparently, reading the literature, some literature are using like a Gaussian unit. Some of them are using SI unit. So there shouldn't be like a 1 over C here, but then that makes the mistake. But since it's a very good language model, that they have the capability to correct it. So I asked further. I said it could be having some mixture and with the units, is that possible to double check? And then it turned out it just started from the even very beginning in terms of the minimum coupling, and then derive the same thing step by step. And if I'm not mistaken, I think the final form becomes correct. So I hope a tool like this can definitely support our physical science research.
Oh, this is all done on ChatGPT?
Yes. Yes.
What class are you teaching right now, Sean?
205. So now I can use that.
Okay. Yes. And then one thing, just a quick heads up, what I will not talk about today too much is the importance on accuracy and how to reach that kind of the accuracy. So imagine if we are in some computational material science this seminar, and then that is something we will talk a lot more. But thinking about for machine learning community, the accuracy is really about the lifeline. Imagine if you are doing self-driving cars, even like a 99.99 accuracy is really, really worse. We cannot afford a very tiny error. And this is an example, the CFAR10 database that contains just about 60,000 these images, like what you see here, classified into 10 different classes: horses, deers, birds, cats, things like that. And then the goal is to develop a way to just use 80% of them to do the training, and then another 20% to do the test, and get the accuracy. Here are a few state-of-the-art. As you can probably see, 2022, there's one model get to the 99.49, and then 2023, there's another model get to 99.550. And then that's the accuracy increasement becomes really, really very hard to even increase a tiny little bit. But still, I think for physics community, people may care a lot more about the implication. What can this model do? And for that reason, I will delete many these details of how it reaches to the high accuracy when you see some algorithm. But if that's something you are interested, we'll be happy to talk more and the offline. Regarding to the field in quantum materials, comparing to the machine learning in the machine learning community is about some additional challenges, such as the volume of the data. because there are not so many of this volume of the data in quantum materials, that's definitely pose a challenge for the data-driven approach. The other thing is, I don't know the right name, but let's say call it a quantumness. To what level of this detailed quantum correlation and entanglement we need to consider in order to correctly capture the material's properties. And for many kind of the systems, and if they are sub-DFT level effective field theory, then even molecular dynamics, and that can really just getting very high synthetic data. But then for many this method post-DFT, like what we talked today, like quantum Monte Carlo, it can be really, really challenging. Then the third dimension, they may not even necessarily to be orthogonal, but for simplicity, just drawn in this way, it's really the curse for dimensionality. For many kind of the problem, and it's really the classification and the yes or no question. But then for many kind of the quantum materials, if you have a wave function, and then that's also have this exponential complexity and becomes very, very high end. So in short, we can consider the challenge to do machine learning on quantum materials lies in this distance to the origin. The closer, the easier, and then the farther away, it's harder to perform machine learning. That's why if you look at some successful examples, such as the pharmaceutical molecules, and they have kind of the billions of the data, so very high data volume, and that's relatively easy to compute the properties without considering strong correlation. And in many times, they just want to do simple classification or regression. It can be very successful for machine learning. On top of that, if you're thinking about another front, like lithium-ion batteries, the energy materials, onto that match of the data, but still relatively high data volume, but then most of the time, the density functional theory is good enough to capture the properties, and then still very successful. People have been finding new this kind of the battery materials and new electrolytes in that field. And for that reason, in order to do machine learning for quantum materials, our strategy or trick is to not to stay too far away from all the three axes at the same time, but at the very least, to just stay close to one axis at the very least. The first example is a way to use the simple spectra to determine topology of a material, and that is actually the simplest example in all three axes, and you can stay close to origin as a starting point. To see the motivation why that becomes a problem, so the topology in the past decade and has been really become a front in condensed matter. There are many these new results have been demonstrated, like the quantum anomalous Hall effect with the dissipation this spin polarized current. That's also the part why the Haldane got the Nobel Prize 7 years ago. And some other effects such as the topological this diode, and that is very different than conventional diode. So this is like the barrier curvature dipole. It's possible to use that effect to harvest this photon energy without the lower limit, like the band gap, but all the photon frequencies. Then there are also some other research and using topology and to maintain very high electrical conductivity using these topological bands, and then also generate very high entropy from other bands in order to do the energy harvesting. But with all this kind of the thing in topology, they can be used. The challenge is actually the step before to use them, is to determine topology. Even the simplest case to tell if you're given a material whether or not it contains a certain kind of the topology. Because topology is not, it's more like a mathematical concept than the direct measurable. One typical approach, and for the band topology, is this RPAS, and with all these electrons, photons come in, and then collect this energy and momentum distribution of this photon electrons. And that's one example from this topological wire semi-metal, and you can directly compare from DFT calculation and to the RPAS results. And the challenge here is related to this RPAS technique, because it involves with electrons. That's why it needs this very high vacuum, and then this also needs a really atomic sharp this surface, and in order to perform the spectrum. Thinking about if you want to do something much simpler than RPAS, the RPAS can be considered as something like X-ray or this UV photon comes in, and then the electron comes out. The X-ray absorption is much simpler. It's like you have X-ray comes in, but then nothing comes out. That's why it's limited its use for quantum materials research. People have been using that to do many different research, like energy materials, even biochemistry. And then the situation, but the limitation for the technical part is much fewer. You don't need a high vacuum, and you can put it into many different kinds of sample environments. With that kind of the background, how to use like X-ray absorption, like the half RPS, in order to detect the topology. So thinking about the structure of the data, the first thing to label the data for all kinds of the materials and with a certain kind of the topological class, and they are labeled as like a topological insulator or topological semi-metal. And then for all kinds of this material, they are also having corresponding X-ray absorption spectra. Because this X-ray absorption spectra has been widely used for energy and chemistry, then this database has been already well tabulated. And what we only need to do is to really do the intersection between X-ray absorption database and topological materials database. And then imagine that if you have a three-dimensional data structure like that, with a different layer from the third dimension as different this chemical element, different absorption edge, and then another axis are just the different type of materials, and then the third one is this different spectra. And then what you can do is to really label them in a topological class, putting them into a different material, like machine learning this architectures. In this particular case, a convolutional neural network, and then in order to see whether you can tell a material is topological or not by using the X-ray absorption spectra. Not even all of them, but one or two or three of them can also be possible. So what we found, certainly it is possible, but it's interesting in the way that the machine learning are analyzing the data very differently than human being. Because of this convolution layers and different this kind of the chemical elements, they will be like a mixed altogether. And turned out that kind of the mixture and become the key to improve the performance. That means intuitively it's possible, because if you have like a calcium that's close to oxygen, then these two spectra, they are not independent, but they are like correlated. And the machine learning can exactly try to pick up that point from there. So that's why for the ternary like a classification, to tell whether a material is topologically trivial or topological insulator, TI, or topological semi-metal, TSM, and then you can reach eventually to over 90% of the accuracy. And then based on this kind of the classification, you can do a little bit further in order to test some kind of the material using experimental X-ray absorption data, and then try to find out the corresponding topological class, and then even try to do some mislabeled these topological materials in a database. But then one question, and that will be haunted us, is that it's not perfect. If you do RPS, you know exactly for sure 100% that material contains a certain type of topology. Even 90% is not a bad number. How to use it? How to use that to do topological material screening? Here is one approach. What we can do is, rather than focusing on one material, is to focusing on a whole bunch of the materials, like here. And this is a list of the predicted materials that has a high chance to be topological. And then after this kind of the step, what you can do is to do the further down screening, like a more refined like DFT calculation, in order to show the corresponding topological class. And some of them you may recognize as known topological materials can be found in this way. But the nice feature here is really not about studying one materials, but aiming for materials discovery and for the broader types of materials. That's something and we did a few years ago, but at the starting point when things can be good, close to origin. And now soon for quantum materials, things are getting more and more challenging. Even we stay with the simple classification problem, how can we tell and to classify something, and if there's a very low data volume? And that's another example and related to the topological quantum computation. And the question is very straightforward to address. So this is a semiconductor and a superconductor hybrid structure. And after an in-plane Zeeman field, and then there's supposed to be the two Majorana zero modes at the end of the semiconductor wire. The question to ask, and from this scanning tunneling spectral data, can we tell and whether this denotes the wanted topological qubits, the Majorana zero mode, or some other swirl signal, like some undriven bound state or some other, there are a few other disordered states over there. So if we only look at the spectra and they look very much like the same, that's why in the community there has been some heated debates. There are a few articles have been retracted and for different reasons. But there's one comment at least we can share back a few years ago from Sankar Samas from Maryland. He mentioned, unfortunately, a consensus seems to have developed that all they observed this this voltage biased peak are trivial. They are not from the Majorana, but from some other trivial states. But this statement is strong. But then what we wanted to do is to provide some less human interfered and less biased approach to either back off this this kind of the statement or try to prove that it's not the case. And then this is the overall workflow in order to show whether we can tell this is from Majorana or not. The first thing, there is no ground truth, even from the experimental data. But one good feature for this particular spectral, scanning tunneling spectrum, is just like the diffraction or some small angle scattering, is the possibility to directly compare theoretical calculations, the theoretical spectrum, and to the computations. This is how people doing this superconducting gap functions using STS, and then studying many other systems. And then by using this Hamiltonian and in this 1D P-wave Hamiltonian and scanning different parameters, by adding noise to the data, we try to justify that a simulated data can mimic the experimental signal. And then what you can do is to apply different machine learning algorithms in order to tell whether it's possible to solely just to tell the class from this signal. And one axis is the Zeeman splitting, one is from this voltage bias from the behind, and then what's the origin of the measured data from there. And because this is not the ideal way, but to us, there's really no other way to go forward without the ground truth. But even before that, what we wanted to do is one more step, is the so-called topological data analysis. The goal for this kind of the analysis is to tell whether or not this problem is intrinsically machine classifiable. Imagine if you are having a Hamiltonian, and that Hamiltonian is parameterized by different parameters, and then for each kind of the set of parameter, that is like one data point in your this parameter space. And then there are many sets of the parameters. They form your whole data set can be used for training, and they are also labeled by the class. In topological database, it's not really about whether each individual data point belongs to which classes, but it's really about the inter-data relation. Imagine if you can perturb the data from one point to grow it into a ball, and then different this neighbor data points may also grow into a ball. Eventually, if these balls are growing to be connected to form a ring, and then you will think that some burst of some kind of the level 1 structure become generated. That's why the feature 1 gets burst. And then imagine if you have kind of the sphere, when this all the data becomes a ball to become a whole closed sphere, a feature 2 will also be generated as well. And then there could also be that if you further perturb the data. So that's the approach, and even without implementing any specific type of machine learning model, and you can tell from the topological case with Majorana zero mode and the other topologically trivial case, they behave very differently in this topological, this latent this space, and that builds the confidence even before building even a linear classifier. Intrinsically, that puzzles people. And these two are harder to classify, is a machine classifiable problem. Then with that, the rest becomes more straightforward for the different sources, like the topological case.
No,
Yes.
So what's the answer? The Copenhagen's result was correctly retracted or is wrongly retracted?
In one slide, I will show that.
Okay.
It's a very good question. Yes.
And what about the one by Ali Aslani's STM work?
It's also shown in a different way. Any other questions? Okay. Yes. But basically, for the ternary classification here, for the topological class with the noisy data, you can still reach to over 90% of the accuracy. And then these are the two common subverse signals. And then you generally get roughly 90% of accuracy in the confusion matrix. That's the answer and for you. And so this is the results we take from this like over 10 different literature, directly just digitize them, and then try to use the model to predict and whether they are topological or trivial. And then there are two kinds of the data. One is the 2D data, meaning that you change the magnetic field and also change the bias voltage. So you have the two axes. The 1D data is simpler, just without the Zeeman field, just change it in one axis. And then in both cases, interestingly, there are a number of the literature. In the paper, we mentioned what they are, but I didn't want to highlight what they are. And then some of the papers, somehow the model strongly suggests that they are not Majorana. So the confidence to predict the Majorana is almost zero, no matter how we play around. So that's kind of to agree with Sankar Dasama's this assertion that many experimental observations are not from Majorana. But then if you look at the data that really passes through both strongly, and is only like here the data number 2, and data number 2 is the one to really far above this bar, and in both cases, and I didn't say here, but that's the only result is the result you mentioned. That's the paper that's retracted from Nature. Copenhagen, yes.
The data that you analyzed, was it the manipulated data in the paper or the not manipulated data?
The original paper. Yeah.
That's the manipulated, right?
Yes. So it's very fun.
They manipulated the images.
So did you use the manipulated image or the raw image?
The manipulated image.
Then
It's more consistent because the real image is only known after that from the other paper and the follow up. So not the original paper. Here we are seeing the original paper that only have the manipulated data.
Okay, so did you get a copy of the unmanipulated raw data?
Yeah.
And then what happened?
The confidence dropped. But we didn't try to highlight that point.
So the paper was retracted correctly. Should be retracted.
That's a very sharp question.
Okay.
Yes, at least from the model, which is a very simplified model and with a very limited this Hamiltonian space. But yes.
Which one is Alias Dani's data paper?
It's also one of them. And
which one, left or right?
Both, because they have both 2D and 1D data.
Okay.
This paper we already published, and so you can track down easily. But we try to not to. We are not even Majorana people, but we try to not to offend the whole Majorana community. But that's I think what we found quite interesting, and that's the data from the retract paper really is the best. And okay.
The noise that you're putting on top of the model, is that sort of breaking symmetries, or what kind of noise? What's it doing? Because I mean, there are all sorts of like screening effects and so on.
Yes, that's a very good question. So basically, when you have a Hamiltonian, and then you can do the quantum transport, and you can get the DIDV curve, the quantum transport,
right.
And that is a very smooth curve. And we try to add various types of the noise on top of that data. And normally, what you see is that when you have noise, then the accuracy for the prediction and then will be reduced, but not much. But then the good thing is that the robustness and the generalizability will be much better. So all the comparison, what we are showing here, and in this case is the one without noise, which means you use the clean data without adding synthetic noise to do the training. And then, but in the paper, we have the one with noise, and it's pretty much the same, and it doesn't change in a fundamental way.
But does the noise change the topological nature of it? Because if it doesn't, then obviously the topological state is going to be robust against it.
Yes. So does not, in the way that quantitative number will be different, and then the one near the 50% is like hard to say. But then some of the one with really low confidence is really low confidence, no matter how much noise you add. So those papers somehow the model at least tells strongly against to consider they are Majorana. Even by bare eye, you look really similar. And then and some other things they also state the same. So the noise is like not a deciding factor in this case.
Your algorithm has been calibrated, I assume. You take one with the correct classification on the topology, and then you just mess it up with noise, and then use your algorithm. You can identify correctly which one is the correct one, right?
Yes. Under the assumption the synthetic data, even adding noise, and with the Hamiltonian model can represent the experimental data, which people already in the community did that, but under that assumption, yes.
You get 100% reliability of your classification scheme.
No, not 100%. That's still in the previous slides, so you can consider it's really, let's answer your question, with noise and without noise, and it's pretty much similar. It don't change a lot, but you can consider it's roughly 90% or something slightly over 90%. If you don't care what kind of the disorder, what kind of the trivial state they come from, then it's slightly even higher. Doing binary is easier, but it's never like 100%.
95%, that's pretty good.
That's the situation. Yeah.
I don't think you can do better, right? With your STM.
Okay. So that's what happened in this particular case. Then how about the dimensionality? In the previous two examples, what we are talking is like the classification, ternary classification in both cases. In this particular case, the best scenario one day we are hoping to really learn is like the wave function itself, but that's like the higher dimension. But today, what we are focusing on is the four-dimensional data in this momentum and energy space on this lattice dynamics, the phonon dispersion relation, which we are hoping to help the design on this thermal transport and many thermal-related applications for waste heat recovery. The architecture we are dealing with is related to graph neural network. And the one reason to see the graph is the huge flexibility. Imagine that if we have the kind of the image or the text, that's already like a very fluid this structure. But then if you really look at the unit, it's kind of this rigid. Text is like a one-dimensional data, one word comes after the other. And that's the part that helps the attention mechanism in order to do even their two words are separated apart. The 1D is the key. On the other hand, for image, it's more like living in a two-dimensional grid, and then one neighbor and is connected to the neighbors. So if you know there's a nose, then your eye is not far away, and that also helps like a convolutional neural network. Graph can be considered as a generalization of this 1D or the 2D grid, like the social network. Two people get to know each other, they can know the third person, or you can consider the past few years for the molecules and the solids. Because for all this kind of the situation, the molecular structure, the atom can be really represented by the node of the graph, and then the inter-atom, this bonding, these relations can also be represented as the edges of the graph. That's why the graph becomes a very natural this representation for your molecular and the solid state structures. So how the graph can transform the materials representation? To give one example, here is one like even not so old, but they call the Coulomb matrix this representation to encode a molecular structure. And this is just to try to convert one molecular structure into a matrix. In this case, the matrix like the diagonal component is like some on-site energy. On the other hand, for these two atoms, then this off-diagonal site between this I and J atoms, they are their Coulomb interaction. The benefit for this kind of the structure is this invariance. Even your Ri and Rj, they are rotated, then you still get the same Mij, the matrix element. Then if you calculate the eigenvalues, and then you can compare the similarity between two molecules, whether they are the same or not. But the graph, as we mentioned, it has a huge flexibility. For example, if you have the graph nodes, and the nodes are like atoms, and then you can put anything you want into of this atomic feature. In this particular case, all the atoms are represented by a very long vector, and the first component is saved for hydrogen, the second component for helium, something like that for periodic table of elements. And then you can also put a number there. You can do like a 1 hot to tell whether or not one atom is there, or you can just, in this case for us, to do phonon, just to put a number, like the mass of that atom in that particular case. So that saves this for graph nodes. How about the graph edges? That is related to this interatomic this bonding relation. In the graph neural network, what the people have been treating on this graph edge problem is to try to encode the two information. One is the distance, and the other is all this the angles. And imagine if you have one center atom, and in here, like this atom A, and then you can draw a vector to another neighboring atom B, and then you have a certain kind of this this angle from the spherical harmonics, and to encode this angular information, and that also ensures you will have this O3 symmetry. And on the other hand, for this radial this direction, it's also possible to encode into a neural network depending on this radial distance. And then imagine if you have a graph node, this atomic feature we showed the last slide, doing a tensor product between all this kind of thing, you are propagating from one layer to the next layer. And here, just like the summation, and for the convolutional neural network, you sum over all the neighboring pixels. Here, you sum over all the neighborhood atoms. That becomes, in the past few years, extremely popular in order to represent the materials with huge flexibility and encode this crystal symmetry, and from that there. And a little bit more detail, as we'll explain, is the key step related to the tensor product. If you look at the conventional neural network, and then like the fitting, consider input data X, try to fit to get the data Y, W and B, this is like the fitting parameters and learnable parameters. And then this is just a regular like this matrix and vector this product. In the graph neural network, and this kind of the tensor product becomes very, very popular. So imagine if you have two kind of the channels, what they are doing is to really do a tensor product between the data and this kind of the weight, as shown in here. You have some kind of atomic feature, and then doing a tensor product to this encoding related to the atomic distance and atomic angular information, and then go to the next layer. And then intuitively, why they want to do that? Why this kind of the tensor product becomes an essential process in graph neural network? So here we come up with one simple example, and from this this education perspective to see why this tensor product is not only try to give people a hard time, but it is really absolutely necessary. Thinking about in this example, you have two electrical charges, and you want to compute, you know, the distance, you want to compute the force between that two charges. To do that, and that's the simplest Coulomb's law, but then you need two information. One, you need this charge number, the Z1, Z2, and that is like a scalar, so it also have even parity, so 0e. That is the scalar for that charge. On the other hand, you also need to know the spatial location of that two charges. That is a vector, so it has all the parity. 1, 0 is also the data structure to do that. So even in this Coulomb's law analytically, you can directly write down their formula. From machine learning perspective, even represent one single charge, you need two different this kind of the these objects with a different structure. But finally, if you have the Coulomb force, that is a vector, so it is a 1, 0. And here is how this graph neural network, and in order to think about this problem. The challenge is that we really want to do in the equivariant way. Imagine, as we just see in this animation, the two charges, the spatial location are just rotated or shifted or just even flipped, and then you know that this force will be staying the same. Is there any way to really tell, like the computer and this equivariance is maintained to make sure that this F will transform like a real vector if the two original position vectors are transforming as a vector and the charge number are transforming like a scalar? So to start, we first need to represent these two charges. As we mentioned, they need two information. The blue one is the charge scalar, and then the position is a vector. And then what can be done here, if we don't do it in a tensor product way, but a naive approach is to propagate from one layer to the other. The two scalar can propagate to become the scalar. The vector can go to the vector. But we know that's not true physically. Physically, the force is really like a G1, G2 over R squared, and that's really depending on both the charge number and also the position. And that's why the tensor product becomes very powerful in this case. Imagine if you have two charges, each one represented by 0e plus 1o, do the tensor product, and then do the tensor decomposition. And then finally, there are a few channels, including the 0e, 1o, and then even this second order, this 2e channels. And then because eventually we want the force we want the magnitude, which is the scalar 0e, and then you can put that 0e channel. If you look at where all this comes from, that's from the direct this sum, and that also comes from this tensor product from them. All the input information will be used to determine the magnitude, and then all this information will also be used to determine the this vector of that force. That's why if you look at the graph neural network, this kind of the tensor product becomes everywhere. So this is a more detailed structure in our model, try to predict the phonon density of states and try to encode your atomic type, that's the atom, and then whenever you have interatomic relation, it's constantly included in all this kind of the convolution layers. And finally, it turned out in this way, you can save the need of the data by a factor of 500, and at the end of the day, what you build is a model. Your input is your favorite structure file, like the CIF, ABC, that's kind of the structure data. And then the model will convert your structure data into a graph. And then the output will be, in this case, the phonon density of states and a curve like this. For some kind of the elements, they can predict really well if they have seen that element and in the training data. And for some other elements, whenever like a phosphorus and the fluorine, and we don't have much training data in that atom, then performance becomes like reduced. But the benefit for this kind of approach is speed. Even for some very complex material, in this figure is a doped glass with over 5,000 atoms, and then you can generate the density of states also very fast in your even personal computer after the training, and then in a few seconds. So that's why our collaborator from Oak Ridge National Lab built this graphic user interface in order to help the neutron scattering users to predict the phonon density of states directly from the structure.
But you are not advocating this can be a replacement for ab initio calculation.
We are not, and I think that's the challenge. I believe unless the accuracy can be the same, which we have some.
Did you compare the two to see if what's the agreement?
So yes, in all these curves you see, all these black curves are ground truth from the ab initio density functional perturbation theory.
Okay.
And we set up some criteria. You can imagine these are the 4 error quartile. And then you roughly, I believe this 80 to 85% of the agreement are good enough to predict many physical properties. If you only care about the scalar like phonon lattice heat capacity, then it's also good, but still it's not ab initio. The accuracy, there is an information loss. But the benefit lies in the speed for material screening. And so in that particular work, we want to find out something for thermal storage. Then you want material with very high heat capacity. Then that's when you can screen down. The artificial, the final number is not accurate, but then the material is not far away. Feel free to stop me any second. Any other?
Just one question maybe on that. So you get the density of states. What about the dispersion? That's a much more difficult problem, is it?
That's we are going here.
Oh, sorry.
Yes, don't be. That's a great question, and that's what we felt sorry after we did the dense of states. We kept thinking how to do dispersion, and that took us another 2 years to figure that out in graph neural network. This is a great question. Anything else before we? So then the question, how can we directly predict phonon dispersion from atomic these crystal structures? If you look at this conceptual process, and the prediction is more like that. First, you input a crystal structure, convert that structure into a crystal graph, and then each atom is labeled by a kind of this feature. And as we showed it before, and this is a very long vector. Eventually, after passing through the different graph convolution, aggregate them, the final feature, and it's a fixed length vector. And that is not good for like phonon dispersion, because for phonon dense of states, you can certainly bin the different frequency range, say by the 100 bins, and then to fill in the number, so the final prediction is like a fixed length vector, 1 times 100. But on the other hand, we know that if we have m atoms per unit cell, the end of the day, you have 3m phonon dispersion, these phonon bands. And that is depending on your input, how to endow this kind of flexibility to the graph neural network. So that's why we propose this so-called virtual node graph neural network. What we know is that even though for a while people are comfortable to see that these graph nodes are atoms, but they are not atoms, they are still graph nodes. So in this particular case, what we are doing is that to use the real nodes to denote the real atoms, but then to use this V, the virtual nodes, to denote collective excitations. And then during this graph convolution process, the real nodes can talk to each other like the old convolution, and then to propagate to the next layer to get the training results. And the key here is this this direction, the information passing. They only allow information or the stored value to predict from the real nodes to virtual nodes, but not the other way. And certainly the virtual nodes can also optimize to each other, propagate to the next layer. And then the end of the day, depending on how many virtual nodes we add to the graph, and then we can get the output depending on this virtual node number. And then that is possible to get at least 3m these phonon bands. That's the first step. This is the easiest, this virtual nodes. We termed the vector virtual nodes, putting 3m, this virtual nodes directly in terms of the crystal graph. And then for many kind of the simple solid, you can get some prediction. Then for some very complex solid, if you look at here, this number just becomes more. Even the best performed tertile and the performance is getting pretty bad. And the error distribution for complex materials is also very high. And even the average phonon frequency does not fall on this diagonal line on the ground truth. So that's why the first thing we wanted to do is to improve the performance for this simple virtual nodes. The situation is that if we ask where the phonon dispersion or the phonon and these other values come from, they from this dynamical matrix. And in this particular case, rather than doing like a 3n virtual nodes, it's possible to do the 3n by 3n virtual nodes, putting it like a matrix structure, and then whenever there is a crystal graph found in, and then you can try to predict all these 3m by 3m values, diagonalizing them, doing this square root, and then predict the phonon values. Turned out even though the number you need to guess is more, but then because the dynamical matrix is more fundamental, closer to the false constants, then the final prediction becomes better. For some simple solid, you can get the phonon energy. All these are for gamma phonons. Even for some complex solid, it's getting better. The average phonon frequency also started to fall along this diagonal line. Then back into the question, how about the dispersion? The real challenge here, we were comfortable to use the real space graph neural network, and then everything is in real space. And then we know that we want to build one with the correct Brilliant zone and in reciprocal space, and how to do that. So it turned out it can be done also in a real space if we consider other neighbors. Imagine if you have a Rubik's cube, and then you have a center unit cell, and that's the one you have the original this matrix virtual nodes, and then try to shift that unit cell to all its 27 neighbors, including itself, and then for each kind of the shift, you have the exponential and time the shift factor, and then you get the k dependence. That is different from the real DFPT calculation. Ideally, to get the real dynamical matrix, you need to sum to the infinity. But in this particular case, this is not a real dynamical matrix, only sum near to the nearest neighbor. But because you know the crystal unit cell right, even by doing so, the brilliant zone can also be done correctly. So that's how you can get to see this prediction, which are the blue and orange curves, can also be compared to the ground truth from density functional perturbation theory calculations. And for many kind of the features like the phonon gap, and then for some group velocity can also be reproduced. One kind of the main advantage to use the machine learning approach under the consideration to sacrifice the accuracy is the speed. So imagine for some people trying to work on this energy harvesting thermoelectric materials, and that could spend even a few years to get even this curve and to calculate the stopping dependence. That's something to use the virtual crystal approximation. What the people do is to build a virtual crystal. For that virtual atom, the mass is the average mass between two atoms A and B with this alloying ratio X. Then this potential is also weighted average. In the particular case, for the machine learning approach in the graph neural network, what you can do is to directly put in different atoms, because the different components represent different atoms. If you turn them on simultaneously, that will represent these two atoms coexisting in one site. And on the other hand, then you put in different numbers, that is like the mass also getting weighted. But by doing that, you can even directly predict some high entropy alloys phonon, and without doing this brilliant zone, this unfolding and process. And there are some other more like orthodox approach and to do like a phonon dispersion using machine learning. One of them is like a machine learning force field or machine learning interatomic potential. In that approach, the interatomic potential are from the machine learning, and then to get to the phonon dispersion, you need to compute the first order derivative to get the force, and then to get the second order derivative, the force derivative, and then do the Fourier transform, and then get the dynamical matrix, then get the phonon dispersion. So that's from the state-of-the-art machine learning potential, and to compute the speed for the average with different atoms. For this particular approach, in terms of the this machine learning, this virtual node approach, because it directly gets this virtual dynamical matrix value, then the end of the day, it skips the derivative step, skips the Fourier transform step. So consistently, it shows about two orders of magnitude speed up, and with the overall m² complexity. So that's why if you have even like 100 atoms, then you can be like a million times faster compared to some ab initio approaches. So that's the part, and we are trying to address for phonon dispersion. In the last few minutes, and we want to quickly go over on a different topic about generating new materials from the generative model. So from our existing cases, that's like a regression or this classification to tell if a data point is a dog or cat. The generative model is from a distribution to really generate a new dog or a new cat from there. In the past few years, except this year, and there's some other newer approach called the flow matching come to replace diffusion model. And the diffusion model has been really the dominant generative approach to generate a high quality synthetic data like image. The general idea is that if you have a data here, you can vectorize them and X0, gradually noisization, eventually to the full noise. And then you have all the training data, and all the training data will help you to do this inverse process and to fit all the parameters here to do the denoising process, and eventually to get back to this image. Then you just generate a new noise, and then eventually it will get to a new like image of the human being. But the challenge for here is how to put a constraint in here. Our motivation is to try to support a quantum materials research like a quantum spin liquids with very few candidates exist, very hard to test experimentally, except for you, and I think it's a very piece of cake for you to detect the quantum spin decrease. And the computation is also extremely challenging. So that's the general philosophy. We want to build the model, but then there's no any kind of the candidate, and then we need to collect the material of database. I think if you can test more materials, we'll be able to have a database, but not there yet. So here is the approach, try to generate new materials with the geometrical constraint. We were focusing on the so-called Archimedean type of the lattice, each atom to the neighbor, and they have the same number of this length. And in this particular case, some of the famous like a triangular, honeycomb, and Kagome all belong to that Archimedean type lattice. In order to do the diffusion model, you have this beautiful crystal structure from the stable materials database, gradually do this noise addition, and in the end of the day, become the noise data. And then what we put is another like a constraint channel, and which is the geometrical constraint. And then after the denoising process, it's like a mixture between the constraint part and also the unconstrained part to put in the total part to the next layer to the denoising. By doing it in this way, the end of the day, the generated material will guarantee to fix a certain type of the geometrical pattern. Like in this case, and you want to generate some triangular lattice materials and with a triangular site for the gadolinium atom, and then but you start from some random noise. So this is the example, and the random noise is like a different type of atom, different unit cell, but then we put the constraint in it, and then after the denoisalization, all the atoms and unit cells are constantly changing. You can choose to relax them by the end of the day, and you will see there's a like triangular lattice in this gadolinium atom in here. And then you can do that to other types of the lattice, like the Kagome lattice as well, and then with other kind of the lattice. What we found interesting before this kind of the common lattice is that there are also some other types of the Archimedean lattice, like this snub hexagonal, and which is like one site missing, so each one only have 5 neighbors, not like a triangle, more frustrated than triangular lattice. And then there are some materials seem to be stable, can be survived the DFT this test, and then some of this like spin ladder structures, and then can also have many stable material candidates. And then we are also hoping to cover more and to use that to support quantum materials. A very quick summary here, without challenging.
Go back to there.
Yes.
Did you recover the prediction for ruthenium and trichloride?
That's a very good question. We can, but no, in a way that for any known material that mainly being used for training. So this
so you cannot predict.
The chances for that is extremely low because you generate from noise, and it's very hard to control the product. You can put this hexagonal and the ruthenium atom there, and then you can even put the chloride there, but then you guarantee to get that material, but it's not quite subsiding.
So basically the idea is the current approach, the Plump's approach, he has the experience, he has the knowledge, and then he can guess the next material. What you are trying to do is build a program to replace him. That's the idea.
To work with him. Because it's still very hard. The forward process is very fast. After the model is trained, you can easily generate millions of materials. Google generated like 2 million new compounds. So in our case, we try to generate more than Google, so 8 millions. All of them belong to some kind of the Archimedean lattice structure. One particular additional is the deep lattice. Also, we found interesting, supporting flat bands. And then we have a down screening process, and then doing the high throughput DFT. Many of them survive the DFT. But then even we throw this to our experimental collaborators, it's still crazy and how to work on them. Then we do have some people help us synthesize the 3, but none of them are quantum spin liquids. So then we are still trying to figure out for longer term, if you can keep generating even multi-millions of materials, what to work on, what material can have the best property for future computing and energy and all that applications. So that's the part, and to conclude, and whenever there's a dimension, or you can use symmetry to address that, even low data volume, and it's possible to use the generative model to also compute that. And with that, I want to stop here and with my group, and thank you for the funding agency. Thank you very much for your attention.
Thanks, Mingda, for a great talk. We have time for some quick questions. Any more questions? Maybe anybody else first? Yeah.
So in the beginning of your talk, you mentioned a variety of methods used for quantum history physics things, and then you mostly referred to DFT or DFPT throughout the talk. So have you done work with other methods, or is it basically just DFT at the moment?
The one for the Majorana part basically is not a DFT, but really just numerically solve the Hamiltonian, and but still it's like solvable. And I think some more challenging is like a quantum Monte Carlo or the exact diagonalization, and then how to accelerate that will be even more valuable, the problem to address.
So we're gonna ask one quick question. So it's really nice to show that you can have all these possible different stable crystal structures, but like if you wanted to, you tell me this combination of elements will give me some certain crystal structure. But if I actually want to make it, I don't know when I mix them all together and then I like heat it up and melt it and cool it down, it will actually precipitate out that compound. I need to know the phase diagram of like a ternary or quaternary phase diagram, and that's a really hard problem. So is there any hope at machine learning to predict out phase diagrams, like if I even a binary phase diagram?
Give me 2 months and I will.
2 months,
So
okay.
we are on the good shape to do that. It's not easy, but we get the data from ASM and the CalPhi.
So we often maybe look up in the old tabulated, metallurgy handbooks for phase diagrams, and they're often wrong. It's very hard to measure out phase diagrams. So then,
hoping to chat more on that because we may be already relying on many wrong data in that case. Even ASM and CalPhi, the two phase diagram database, are not agreeing with each other a lot.
Yeah, it's very hard. Yeah, so that'll be interesting. Okay. So, yeah.
How does this fare with the impurities if you have like magnetic impurities or like some sort of?
Yes, that's a great question. I think many people know that impurities is extremely important for properties, and it's still very hard given there's a huge design space. And there has been some very recent machine learning work. Even silicon impurities, they can generate even tens of thousands of the different configurations. And so then if you want to build a generic predictor, so some of the work we show is like an arbitrary material, then it's really a very large space, and how to even generate a reliable training data will be challenging. So I think people really realize the importance of impurities, but then